Okay, so we're going to continue talking about genetic engineering and look at how it's kind of permeated all our lives. Nearly every aspect of our lives, there's some component of genetic engineering embedded into it. So Jurassic Park. Think about how many different Jurassic Park, Jurassic World, Jurassic, etc. movies are out there. They're all connected to or all based on genetic engineering. So I'm going to play a little clip from the first one, and then we'll talk about it and say, okay, is this realistic? Could Jurassic Park actually happen? Is that a feasible thing to bring back a dinosaur? Let's see what some of the scientists say about this, and what is the likelihood that they could or would ever want to bring back a dinosaur. All right, so let me get this going here. Let's move this up. Expand this out, and I'm trying to fit this into the screen so it's a little better to view for it. All right, let's see if that works for us. So, okay.
Poinar was researching how ancient fossilized amber trapped and preserved million-year-old creatures.
Theoretically, it was possible to get dinosaur DNA out of a blood-sucking insect in amber. Of course, it had to be one that was greater than 65 million years old.
Poinar was keen to put the theory to the test.
Okay, so something to mention. Remember he said, possible, but the insect has to be 65 million years or older. Dinosaurs went extinct 65 million years ago. They did not exist anytime since 65 million years ago. There is absolutely zero scientific evidence that humans and dinosaurs coexisted. So keep that in mind.
The dinosaurs died out 65 million years ago, so he needed to find an insect preserved in amber from before that time to have any chance of finding some dinosaur DNA. After months of searching, he got lucky.
I was looking at it and I said, oh, there's a hazy, dark object inside under some of these layers. And so I began to peel these layers off with forceps carefully.
Poinar had found the remains of a tiny beetle-like creature called a weevil.
When I got very close to the weevil, it fell out and cracked, and tissue came out of its abdomen. And I thought, my goodness, there's some tissue there. I have to preserve that. Maybe that has some DNA.
Poinar preserved the weevil tissue in alcohol and sent it to colleagues for DNA extraction. He was shocked by the results.
We were successful, and we were able to get some DNA out of this weevil, which was then, and still is, the oldest known fossil DNA, dating back between 125 and 135 million years.
Poinar had extracted DNA from the time of the dinosaurs. It proved that if dinosaur DNA could be found, maybe it too could be recovered.
So many scientists were just fascinated. It shows that theoretically, it would be possible to get dinosaur DNA out of a blood-sucking insect in amber.
All right, so we want to think about that. Is that realistic? Is that feasible to do with biotechnology? Is it something we want to do? Is it something we should continue to do? Should we continue to chase that direction? We'll talk a little bit about this when we get into ecology and we talk about conservation of an endangered species. Should we do that with polar bears, tigers, bald eagles, lions, etc.? All these species that are possibly going to be extinct in our lifetimes. Should we pull their DNA, which is readily available now, should we pull their DNA and use their DNA for cloning, genetic engineering, etc.? So once you get a hold of a piece of DNA, you need to organize it and kind of sort it out. So we use a technique or a technology called gel electrophoresis for sorting DNA, organizing it, figuring out what it is, separating it, that type of thing. Now, gel electrophoresis works off of two very, very important principles. That's why I'm writing them out here and using red. Size and charge are the two principles in which gel electrophoresis will organize a piece of DNA. So size, big molecules move a lot slower than small molecules. So if we're in a race and they're both moving, that one may move that far, this one will move a lot further in the same amount of time. Size is critical when you're talking about electrophoresis. Smaller molecules move faster because they're moving through an actual solution. They're moving through a gelatin, which has tiny little holes in it. So big moves slow, things to keep in mind. And then with charge, opposite charges attract. So if you have a positive and a negative charge, those two molecules are going to move towards each other. If you have two positives, they go in opposite directions. So looking down here, if this is the, let's say this is the positive side of the electrophoresis chamber, and this is the negative side, all of these molecules here are going to be positively charged molecules because they're all moving in this direction. Any positive charged molecule will move towards a negative electrode. It's the basis of electrophoresis. So now that we have it in our hands, we can use it for stuff. We can move it, we can separate it, we can organize it. And one technology that's very, very common, you go to Walgreens and get this, is paternity cases. Looking at who is the father of the child, who is the genetic parent of that child, that's using biotechnology, and that's using electrophoresis. So again, this is the movement of molecules is based on size and charge. That's it. Those are the two key features. So when we look at this DNA example here, this paternity case, let's take mom's DNA, right there in the green. And mom has all these different bands going down, what we call banding pattern. I'm just going to highlight a few, for example. And then let's take her child. And the child has, I'm going to use yellow there, has this piece of DNA that came from mom, because it matches up with mom's green one. This came from mom, matches up with mom's green one. I could say this one came from mom, so did that one. Those are all matching back to mom. But there's a couple pieces of DNA there that the child has that don't match back to mom. So that had to come from the father. Half comes from mom, half comes from dad. So we have dad 1, F1. Here's his DNA. And if you notice, his bands are not matching up to the child, or the uncertain child's DNA. This one here, this one here, and the one right below it. Those, as well as those are not matching to F1. They don't line up with F1's DNA, so didn't come from F1. Let's look at father 2. F2. Notice that band matches up right there. This band matches back to that one on the child, that one to the child. These two both match to the child. Somebody may say, well, wait a minute, pause. What about this piece of DNA from that man right there? That does match the child. It does. But under normal paternity situations, F1 is not going to contribute one piece of DNA and F2 contribute the other 5 pieces of DNA. All of it has to come from one father and one mother. Or, let me back that up, half from one mother, half from one father. Even though you look at that red arrow and say, but that piece could have come from F1. No, it can't. F1 and F2 just happen to have the same gene. Maybe they both have brown hair, and that's the piece of DNA for brown hair, and the child has brown hair. That's why they share a common gene. So if we sequence the DNA from everybody in our class, I guarantee you there will be a lot of overlapping pieces of DNA. Okay, so paternity case. It's how they're doing paternity situations today to guarantee paternity. You are the genetic father of that child. Crime scene analysis, same concept. Here's the DNA at the crime scene. Here's the suspect 1, 2, and 3's DNA. Let's see if it matches up. So things to consider. There are pushes and possibilities of creating a DNA database where the government, law enforcement has DNA. They have basically a big file of DNA, and then if there's a crime, they just go back to the database and say, hey, what's in the database? Who does it match up to? Do we see a match? Well, then that's probably the person who committed the crime. So things to think about. Some states are passing legislation that if you put your DNA in the database, let's say you get pulled over for a traffic violation, and they may make a deal with you. Hey, put your DNA in the database, we'll basically ignore your violation. And some people may say, oh, great idea. Okay, cool. I don't want that ticket. I don't want that bump in my insurance premiums. But what happens to your DNA when it's in a database? Who controls it? Who controls the privacy of it? Who controls all of that information? Do you want an employer to get that? Could this be a new type of discrimination based on DNA that we see in the future? So things we want to keep talking about, things we want to discuss here. So, all right. So the sequencing of DNA is what helps us determine the order of the nucleotides. So when we use electrophoresis for sequencing, we're pushing a strand of DNA through the gel, and it's going to give us a pattern. And we come back to that pattern and say the first 3 letters, ATA. That equals a codon. That equals a piece of genetic information. There's an amino acid. Let's add that to the next 3, AAA. The next 3, AAC, TCA. And you keep doing this, and now you can figure out what are your amino acids that would be strung together to create the particular protein or trait. So now we know this is the genetic information behind a particular physical trait. This is what, maybe it's normal. If somebody doesn't have the normal trait, we can compare their DNA sequence to this sequence, and then we can try to figure out how do we fix it, how do we resolve it. Or do we identify this early on in life, maybe during embryological development, to say, well, that developing embryo has a piece of DNA that's going to make the protein wrong or incorrectly, and now that's going to lead to the death of the individual. Do we want to continue with that pregnancy? Do we want to try to manipulate the DNA during embryological development? All sorts of different possibilities. The key here is information is now becoming available for us to make these decisions from an educated perspective. Okay, so I encourage you guys, check out some more of Jurassic Park. They talk about how they clone the dinosaurs in Jurassic Park. Kind of a cool idea. Is it feasible? Is it realistic? The other one I wanted to just briefly mention is this company called Viagen. So here's their website, Viagen.com. This company's been around for about 30 years, and what they're doing is cloning animals. So they are cloning all sorts of different animals. Do we think this is a good idea? Hey, let's clone our horses. Let's clone cattle. Let's clone pets. What do we want to do here? So a lot of information here. Do we clone things? Some great ideas, but is this the right direction to go with this? So livestock folks, prize grand champion bull might be $100,000. Do you clone that animal to ensure you have the genetics in the next generation? Or do you rely on, hopefully the breeding's going to work and it's going to give us a very similar individual? So things to think about. good, bad, and some uncertainties. All right, let's talk about more genetic engineering.